Hi everyone. So our second lesson of this unit, 3.2, we're going to look at a different type of series called a Maclaurin series. And once we introduce that, I'm going to talk about doing some operations with series. Okay, so that might include multiplying some together or using them to calculate integrals. Okay, so our first lesson, we talked about infinite series in general, and then we looked at geometric series, okay, which had a common ratio in between. This lesson, we're going to focus on what's called the Maclaurin series. So the Maclaurin series is known as what's called a power series expansion. What it tries to do, and what it does actually effectively, is you try and represent a function, f of x, as a series of constants and powers. In other words, you're writing it like a polynomial. So if you have a function f of x, what we're going to do is find a series that is equivalent to it. Okay, so when you plug in certain values, it's equivalent to it. And what the series looks like, okay, is a constant term plus a second constant term times x plus a third constant term times x squared, fourth times x cubed, and it keeps going infinitely. What you'll see a lot of times is we'll focus more or less on these first four terms. So I'm not going to ask you to calculate out the first 10 terms of this sequence. But basically, it's trying to get you to write it as a polynomial. Remember, back to quadratic equations, ax squared plus bx plus c. That's the type of format that it's trying to get you to write it out as. The reason it's written as a series is because it can have an infinite number of terms. Okay, so just like when we talked about infinite series in the last lesson. Okay, so what this means is you might have a function f of x. Let's say f of x is 1 over 1 plus x or something like that. You're going to write this instead as what's called a power series. So I'm going to show you how to derive this. I'm not going to show you how they've developed a Maclaurin series. That's much more advanced in terms of mathematics. But I am going to show you how to make this conversion and make it rather simply. In order to do this, we are going to need to calculate what these constants are, right? We've got these terms in here. If I just kind of clean this up a little. We have these x terms, and they're just x, okay? X squared, x cubed, just like a normal function. But we have these constants that are sitting behind it. So what I'm going to show you is how to figure out what those constants are. And in doing so, we're going to keep it in this kind of general form. You'll see exactly the form for what a Maclaurin series will look like, okay? So this is going to use our knowledge of derivatives. Okay, so calculating this will use our knowledge of derivatives quite extensively. And remember, we have a function f of x, and we're trying to make it equal to this expansion that's sitting here. Okay? And remember, what we know is if we're trying to solve for constants, oftentimes, going back to when we did integrating with partial fractions, we found values of x that we could substitute in that would remove a lot of these terms here. Okay? In this case, the value of x to substitute in for Maclaurin series is when x is equal to 0. Because let's look at the first instance. If we have just this function, regardless of what it is, it's just a function of x, and it's equal, we're trying to figure out how it can be equal to this power series. If we substitute in x equals 0, we have our function at 0 is equal to our first term, a0. It doesn't have an x beside it, so it's just a0, plus our second term, a1 times x, x is 0, plus our third term, a2 times 0 squared, fourth term, a3 times 0 cubed, all the way to our last term, which is a to the n, okay, whatever that constant is, times 0 to the n. So all of these terms with an x go away. What that means is our first constant can simply be found by taking the function, substituting in 0. Okay, so to give you some perspective on this, if we were converting it, again in our function f of x, going back to it, was 1 plus x. If we substituted in 0, we get 1 over 1 plus 0, which is simply 1. So our first constant here would just be 1. Okay? So it's starting with a function like that. We're going to find these terms. I'm showing you how it's derived. Okay? So I'm going to try and put an example here, which is a function, to kind of show you the in-between. And then we will actually do this with a real function to show you how it fully expands out. To find the first constant by just taking the function at x equals 0. Now I'm going to start taking derivatives of this function, and you'll see that as I take more derivatives, we will be able to find more constants using the same method where we substitute in x equals 0. So our function, remember this is our basic form, is a constant plus a second constant times x, a third constant times x squared, a fourth constant times x cubed, all the way to our final constant, okay, which would be a to the n times x to the exponent n being the number of terms. If we take the derivative of this, right, what we'll see is the constant will go away because it doesn't have any x terms. Our next term is a1 times x. That just becomes a1 because the derivative of x is 1. Our next term, remember you bring the exponent down in behind, so it becomes 2 times a2, and then this just becomes x because you subtract 1 from the exponent. So we're left with 2a2 times x. The third one becomes, again, moving the exponent down and subtracting 1. We're left with 3 times a3 times x squared. That would continue on. Again, I'm only going to show you the terms up to x cubed for this. But it will continue on, and if you took the derivative of this function, you'd bring the n down in behind, so it's n times a to the n. Then you would subtract 1 from the exponent, so you get x to the n minus 1. Now that we have the derivative, you can see the a0 term we already calculated is gone. But now we have a term that doesn't have x again. This time it's the second constant, or a1. So if we again substitute in x equals 0, because we're trying to solve for this function, then what we get is the first term, a1, plus the second term, 2 times a2 times x, which is 0, plus 3 times a3, again times x squared, which is 0 squared, or 0, all the way to our final term, which is n times an times 0 to the exponent n minus 1. So all of these terms that have a 0 in them go away. And what we find out in this case is the second constant can be found. That's all we have left is a1. So the second constant is equal to the derivative solved at x equals 0. Okay? You're going to notice that this is the trend moving forward. So if we continue this pattern, I'm going to find the second derivative. So the first derivative I have written here for reference. It's a1 plus 2 times a2x plus 3 times a3x squared, all the way to this final derivative term, which is n times an x to the n minus 1. If we take the second derivative, all right, this constant a1 will go away, which we've already found it, so it's not a big deal. The second term becomes just 2 times a2 because the derivative of x is 1. So it becomes 2a2. The next term becomes 3, again, bringing the exponent down, we get 3 times 2 times a3, and this becomes x to the 2 minus 1. Okay, remember just using normal derivative rule. So this becomes 3 times 2, a3 times x. And if you keep going, we finish on our final term, which is n times n minus 1, a to the n. And again, this one, all right, just like we did before, we brought the exponent down, and we have to subtract 1 from it, so we get n minus 2. In this case, substituting in x equals 0, again, you see something that happens here. The a2 term remains because it doesn't have an x, but the remaining term, 6 times a3 times x, you substitute x 0 for both this term and the final one, which is just the case with n, so they will both cancel. What we're left with is our second derivative, when you substitute in x equals 0, is equal to 2 times a2. So to solve for a2, we divide both sides by 2. And what we're left with is our second term is equal to the second derivative of f at x equals 0 divided by 2. Okay? We're going to do one more now because we've now found a0, a1, and a2. Okay? So our last term, remember I said we were only going to go to the x cubed term, is we need to find this constant a3. Okay? Again, what you'll notice in these is we can't find them all. We can't go to infinity for every one. But finding the first several terms is usually enough to allow us to approximate these series. Okay? And approximations are arguably what the important part is when it comes to these series. So we're going to find the third derivative now. So we have our second derivative written here, 2 times a2 plus 3 times 2. You will see why I leave it as 3 times 2 later on. Times a3 times x plus, again, our final term here that sits as just n. If we take this derivative again, okay, the 2a2 term is gone because it doesn't have anything with x. The a3 term will remain 3 times 2 times a3. And then all we have left here is this final term where again I take the derivative. The n minus 2 comes down, so we have n times n minus 1 times n minus 2. And we subtract 1 from the exponent, so we're left with x to the n minus 3. Again, this term stays there. You'll see that it's going to become 0 again. When we substitute in x equals 0, the first term will remain because it doesn't have an x. But the last term will again go away because it's x to the n minus 3. 0 to any exponent is simply 0. So we're left with the third derivative at x equals 0 is equal to 3 times 2 times a3. So to solve for this, we have to divide both sides by those 3 and 2. Sorry, I wrote 3 and 3. 3 times 2. And what we're left with is a3 is equal to the third derivative at x equals 0 divided by 3 times 2. Well, 3 times 2, okay, can actually be written as 3 factorial. Okay? And the formula you'll see will be written that way. So a factorial, when you see it written that way, is 3 times 2 times 1. Okay, so it's each of the terms in sequential order multiplied together. 2 factorial would be 2 times 1. If you go the opposite direction, 4 factorial would be 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, so you're going to see it written in terms of the factorial instead, just to tell you what's going to come in the next slide. So we've solved for all of these terms, right? We've solved for a0. Remember, a0 was the original function at 0. a1 was the derivative at 0. a2, remember, was the second derivative at 0 divided by 2. We've written it as 2 factorial, and that's because the later ones, the factorial matters. 2 factorial is the same as 2. The third one was the third derivative at x equals 0 divided by 3 times 2, which in this case we write as the third derivative at x equals 0 divided by 3 factorial. And this will continue on all the way to your final term. Okay, so I showed you the derivation for these first 4 terms, so 1, 2, 3, and 4, but that stays consistent throughout. So the fourth term here would be the fourth derivative at x equals 0 divided by 4 factorial. Okay, continues that pattern. This is what's known as the Maclaurin series. Okay? So the Maclaurin series is going to rely heavily on doing basic derivatives. So we're going to walk through a few examples, and then we're going to use our knowledge of these series to see how we can actually implement them for other scenarios. Okay? Okay, so let's look at an example using this Maclaurin series. Okay, so this is going to show you how it works with an actual function. Again, remember with the Maclaurin series, we're trying to represent this function as a series of polynomials. So find the first four terms of the Maclaurin series expansion of f at x equals 4 over x plus 6. So this is our function. Okay, that's f at x. We can write this, and I'm going to write it this way just for the sake of our derivatives. We can write it as 4 times x plus 6 to the exponent negative 1. Again, moving this entire term up into the numerator. Okay, so I'm going to leave it like that just because you'll see when I start taking derivatives, it becomes easier. When you're solving for the actual numbers, it's easier for it to be in fraction format. Okay, so remember, for our Taylor series expansion, we're trying to write f at x is equal to the first term, which is that function at 0, plus the second term, f prime at 0, plus the third term, f prime is 0, multiplied by x, plus our third term, second derivative at x equals 0 divided by 2 factorial times x squared, plus our fourth term, the third derivative, or f triple prime, at x equals 0 divided by 3 factorial. And this continues on. We don't have to show the last term because we're just trying to find these first four terms. Okay? So we'll start with f at 0. So f at x is equal to 4 over x plus 6. So f at 0 is 4 divided by 0 plus 6, which is 4 over 6, or 2/3. Okay? Our second one we have to find is f prime at 0. So to do that, we have to find f prime of x, which in this case, again, the reason I kept it like this is because we can use the power rule. So we get negative 1 times 4, x plus 6. And remember, you have negative 1, you subtract 1 from the exponent. So I simply move this negative 1 exponent down to this location here. Okay? If you multiply that out, you get negative 4 over x plus 6 squared. Okay? Now, if you substitute in f at 0, so f prime at 0, you get negative 4 over 0 plus 6 squared, which is negative 4 over 36, or negative 1 divided by 9. Okay? So we know our second term, negative 1 over 9. To find our second derivative, okay, we have f double prime of x. That's equal to, starting with our first derivative, we have negative 4 x plus 6. And again, I will bring it back into the numerator, so it's to the negative 2. To find the second derivative, it's equal to negative 2 times negative 4, x plus 6 to the negative 2 minus 1, again using the power rule. And what we arrive at here is 8 divided by x plus 6 cubed. So that is f double prime of x, or the second derivative. So now, substituting in f double prime at 0, we get 8 divided by 0 plus 6 cubed. And what we get for this is 8 divided by 216, which simplifies to 1 over 27. So I'll leave that as f double prime, and then when we substitute it into our final equation here, you'll see that we'll do it with the divided by 2. So last we have our final derivative, the third derivative, okay? F triple prime, or the third derivative of x. And in this case, looking at our previous equation, we start with 8 times x plus 6 to the negative 3. So f triple prime of x is equal to negative 3 times 8 times x plus 6 to the negative 3 minus 1. Okay, one thing I didn't mention here, which I will mention now, is inside the brackets, you would normally have to take that derivative, right? So the derivative of x plus 6. The derivative of x plus 6 is simply 1, okay? Because the derivative of x is 1 and the derivative of 6 is a constant. So I didn't show that in the previous ones, but in case you're wondering, that is why I didn't show that. So if you simplify this derivative out, f triple prime of x is equal to negative 24 over x plus 6 to the exponent 4. Substituting in x equals 0, we get negative 24 over 0 plus 6 to the exponent 4. And what we get for that as our final answer is negative 1 over 54. Okay? So it's always going to be these steps in the Maclaurin series to find these. So it's a lot of steps, but it's taking derivatives simply using the power rule. Okay? So now we can substitute all of them back into this original equation. So what we get is that f of x is equal to the first term, f at 0, 2 over 3, plus the second term, which is negative 1 over 9, which is negative 1 over 9x, so it becomes minus, plus the third term, okay, which we had 1 over 27, which is 1 over 27 divided by 2, remember, because it's 2 factorial. So that actually becomes 1 over 54 x squared. And our last term is f triple prime at 0, which is negative 1 over 54, so minus 1 over 54, divided by 3 factorial, and 3 factorial is 6. So if we simplify that, we get minus 1 over 324, that's just using your calculator, x cubed. So those are the first 4 terms of this Maclaurin expansion. Okay. Again, you could keep going, but I usually stop you at 3, 4, 5 terms. All right. Second example is to find the first 4 terms of the Maclaurin series expansion for f of x is equal to sine of x. Okay. In this case, the derivative of sine x is relatively simple. It's cosine of x. Derivative of cosine x is negative sine x. So if we start with this series, we can actually calculate each of these derivative terms rather quickly, compared to the last example where the derivative took a little bit more time. So we start with our function, right in the formula. So f of x is equal to the function at 0 plus the derivative of the function at 0 times x, plus the second derivative, f double prime of 0, divided by 2 factorial times x squared, plus our final term, f triple prime at 0 divided by 3 factorial x cubed. And I can continue to write the rest, but we're only looking for the first 4 terms. Keep in mind that these formulas, I will be providing them to you on your formula sheet. So they are obviously not formulas I expect you to memorize. So now we know we have to take the function and its first 3 derivatives. So I'm going to do that right away. So we have f of x is just equal to sine x. The derivative, f prime of x, is equal to then cosine of x. The second derivative, okay, becomes the derivative of cosine x, which is negative sine of x. And the third derivative, f triple prime of x, becomes the derivative of negative sine x, which is simply negative cosine of x. So you can see for this function, we could do the derivatives rather quickly. And now that we have those, we can directly substitute in, again, each function at 0. What you need to understand for sine and cosine, and I know we've talked about it before, is understanding the graphs of them. Okay? So at the maximum and the minimum of the plane function, you have -1 and +1. So for sine x, it starts at 0, okay? Goes up to its maximum, back down, and it's a periodic function, so it keeps going, right? So at x is 0, sine of 0 is 0, okay? Cosine, remember, is what's called out of phase from sine by 90 degrees or pi by 2, whatever one you want to think about it. So again, starting with the same boundaries of 1 and -1, cosine starts at 1, okay? Goes down to its minimum and then back up to the starting point. And again, it's a periodic function, so it will keep going. So in this case, cosine of 0 is actually equal to 1. Okay? Important functions, important items to know again when you're solving this. I always like to refresh you on that. So for each of these, we have to find the value at x is 0. So the first function, f at 0, is equal to the sine of 0, which, as I mentioned, is 0. The derivative, f prime at 0, is equal to cosine at 0, which in this case is 1. The second derivative at 0 is equal to the negative sine of 0, which is still 0, right? Because -1 times 0 is 0. Lastly, our third derivative, f prime, I almost wrote x, at 0, is equal to the negative cosine of 0, which in this case is -1 times 1, or just -1. Okay? So you can see in this expression, two of the terms are going to go away, the first constant and the second derivative, right? Because we're taking them both at 0. And you're going to see something similar happen for the cosine function, which we'll talk about later in this lesson. So knowing these, we can now substitute them again back into this original formula. So most of the legwork in determining this series is, actually I'm going to say all of the legwork, is figuring out these derivatives and then substituting. Okay, so once you have that, you substitute them in. So f at x is equal to f at 0, which in this case is 0, plus f prime at 0, which is 1 times x, plus the second derivative, f double prime at 0, divided by 2 factorial, which in this case is 0 over 2 factorial, times x squared. And the third function, okay, f triple prime at 0, which is -1, divided by 3 factorial, x cubed. And again, plus the remaining functions, but I only asked you for the first 4. So if you simplify this, f at x becomes just x. This first term is gone, this third term is gone, so we're left with just the fourth term, which is minus 3 factorial is 6, so we're left with 1 over 6 x cubed, and then plus the remaining functions. Okay, so you can see that this turns out to be a rather simple expansion, and this is actually, if you factor this all, equivalent to the function sine x. Okay, we're going to see why that's important, because it might allow you to convert sine x to a series, and the integral of each of these is far simpler, right? Because the integral of them are actually just using the power rule. Okay, so our third example, again, I'm trying to show you how different functions can be expressed in terms of the Maclaurin series. You're going to see that sine of x from our last example and e to the exponent x in this example will both be showcased in the second half of this lesson when we talk about some of these typical functions, I'll call them, that we see often. So in this example, find the first 4 terms of the Maclaurin series expansion for f at x equals e to the x. Remember, e to the x is going to be an easier one because the derivative of e to the x with respect to x is simply e to the x, okay? Because the derivative of the exponent x is just 1. So its derivative is the same function, okay? So knowing that, we can start by writing out our Maclaurin series. So f of x is equal to the function at 0 plus the derivative of the function at 0 times x plus the second derivative of the function at 0 divided by 2 factorial times x squared plus, again, the third derivative because we're looking for the first 4 terms. So f triple prime at 0 divided by 3 factorial x cubed. And we can add the remaining terms, but in this case, we're only looking for the first 4. So we look at this function, f at x is e to the x. The derivative of e to the x, f prime of x, is e to the x. The second derivative of x is again e to the x. And the third derivative is again e to the x, okay? Because the derivative of e to the x is simply itself. If this was 2x, okay, you'd have to have the derivative of the function in the exponent as well. Okay, in this case, we don't have to have that because the derivative of x is 1. If we substitute in 0 into each of these, we get f at 0 is e to the 0, which is 1. Anything to the exponent 0 is 1. F prime at 0 is again e to the 0, which is 1. F double prime at 0, e to the 0, which is 1. And f triple prime at 0, again, e to the 0, which is 1. So it's the same for all of them. This was probably the fastest one you're ever going to do. So now we can substitute in each of these values. So f at x is equal to f at 0, which is 1, plus f prime at 0, which is 1, times x, plus f double prime at 0, which is 1, divided by 2 factorial, which is 2, x squared, plus f triple prime at 0, which is 1, divided by 3 factorial, which is 6, x cubed. Okay? And we can keep expanding that out, but we only want the first 4 terms. So writing this second term, it's the only one that I haven't fully expanded. 1 times x, if we erase that, simply becomes x. Okay? So you can see this is the Maclaurin series expansion for e to the x. All right? So now that we've talked about the Maclaurin series expansion, what I'm giving you here is several functions and their associated expansions. Now, 2 of these are functions we've already derived. Okay, so we've already talked about e to the x, and we've already talked about sine of x. And you can see that those expansions that we calculated out are provided here. The other ones that I show you for is cosine of x, the ln of 1 plus x, and finally 1 plus x all raised to an exponent. So 1 plus x to the n is a common one that people actually see in business applications for compound interest. So I show you the expansion here. Again, these are expansions that I will provide to you in a formula sheet. I do not expect you to memorize these. The piece that I've added here is what's known as the interval of convergence. And what that means is what values of x this expansion is valid for. So the ones that we've seen so far, e to the x and sine of x, as well as cosine of x, are valid for all values of x. But the last 2 functions, all right, ln of 1 plus x. Ln is only valid when, if you had ln of x, it's only valid when x is greater than 1, the absolute value. Okay, so ln of 0 is undefined, ln of a negative number is also undefined. So its interval of convergence is only when the absolute value of x, in this case, is less than 1. Okay. The same is true for our final function. So 1 plus x to the exponent n is not valid for any terms where the absolute value of x is not less than 1. Okay, so when you get to values that are greater than 1, okay, they're no longer valid. All right. So for each one of these, I guess before I move on, we're going to use these expansions in different ways. So for this section of our lesson, I'm going to use these expansions and show you how we can combine them with multiplication. We can use them and say we don't have e to the x, we have e to the 2x, or maybe we have sine of x squared. So how we can quickly modify this without having to do all of those recalculations of all the derivatives to calculate it for a different e function. And we're also going to see how converting a function to a series can make the integral easier to do, and it can allow you to find approximate answers to integrals that otherwise we wouldn't have been able to solve using the methods we learned in the last unit. Okay, so those are 3 separate cases that I'm going to walk you through. The first case is using a different version of the function. So remember, let's look at e to the x. Well, our function f at x was e to the x. And our expansion turned out to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, on and on and on. If you kept going, you'd have x to the 4 over 4 factorial, x to the 5 over 5 factorial, etc. If the function was instead e to the 2x, well, all you have to do is remember this is the function at x. Okay, so when it's x sitting in here. If we instead have 2x, we can simply write this as f at 2x and substitute in 2x for everywhere we have an x. So instead of x here, we have 2x. Instead of x squared, we have 2x all squared. So both the 2 and the x are squared. And for this term, we have 2x all cubed. Okay, so you are allowed to simply substitute that value in. And if you do that, often it's going to require some simplifying. So we end up with 1 plus 2x. In our next term, we have 2x squared, which is 4x squared, because you have to square both terms. And you have a 2 in the denominator. So this becomes 4x squared divided by 2, which is 2x squared, which you can see here. Okay, it's a bad 2. Let me fix it. Our last term, okay, we have 2x cubed. That's the same as 8x cubed, because 2 cubed is 8, divided by 3 factorial, which is 6. So that simplifies to 4x cubed over 3, which you can see is the term written here. So this is a very efficient way for you to take the basic version of the series and modify it to be a more advanced function. All right? So with that knowledge, let's look at an example. So find the Maclaurin series expansion of cosine x cubed. So starting with this, remember that table I provided to you in a previous slide had cosine of x. So when f of x was cosine of just x, the Maclaurin series expansion was equal to 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus, and it kept going. But this is for x, and we have x cubed. But remember, we can simply substitute in for x cubed. So we can have our function at x cubed instead. And if we have that, we end up with 1 minus x cubed squared divided by 2 factorial, which is just 2, plus x cubed, okay, raised to the exponent 4, divided by 4 factorial. So remember, 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24. Okay? And this continues on. So to solve for this, the one thing to keep in mind is remember your rules of exponents. So if you have x cubed, in this case, squared, so the x cubed is raised to another exponent. When it's raised to another exponent, that's the same as x to the exponent 3 multiplied by 2. Okay, so in this case, you don't add the exponents together, you multiply them. So that becomes x to the exponent 6. Similarly, for the second term, we have x cubed raised to the exponent 4. So that's equal to x cubed, x to the exponent 3, multiplied by 4, which gives us x to the exponent 12. So if we simplify this, we get f at x cubed is equal to 1 minus x to the exponent 6 over 2 plus x to the exponent 12 over 24. Okay, and then I always write plus dot 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 because the series doesn't end at 3 terms. We're only showing it for the first 3. So you can write these as 24 and 2, or you could have also kept them as factorials like I have in my solution. I'm okay with you doing either, right? So now that you saw that we could use slightly different functions and quickly find their series expansions, what we can also do in our second case is actually multiply 2 series expansions together. So let's say we have a function e to the x times cosine of x. Well, that's 2 separate functions, e to the x and cosine of x, which we can write as their own separate expansions. E to the x is 1 plus x squared over 2 factorial plus, and then it goes dot dot dot. Okay, x cubed over 3 factorial, so the fourth over 4 factorial, and it keeps going. Okay, I'm showing less terms here because when we multiply it out, it makes it easier to multiply and you have less terms. Similarly, for cosine of x, we know that it's 1 minus x squared over 2 factorial plus, and it keeps on going. So if we have them multiplied by each other, so e to the x cosine of x, that's the same as those 2 functions multiplied together. So we can multiply those series together, all right? If we do that, then we get, remember, the first function, e to the x, which is 1 plus x squared over 2 factorial plus, and then it keeps going. That's multiplied by 1 minus x squared over 2 factorial plus additional terms, okay? So what you can do is multiply out the terms that you know, okay? Of course, as you add additional terms, not only does it mean that you have more terms to distribute out, okay? So for each of these, for 1, you have to multiply it by 1 and multiply it by this negative x squared over 2 factorial. For the x, you have to multiply it by 1 and multiply it by the negative x squared over 2 factorial. So you have to distribute each of these terms out when you're expanding. So the more terms you add, this final answer might change slightly, but what this allows you to do is it gives you an approximation of this function e to the x cosine of x. Okay, so don't worry about the fact that they're not all being multiplied out. You can take the ones that you know, which is usually the first two or three terms, maybe 4 terms, and multiply them out. If you do that, all right, you get 1 times 1, which is 1. Okay, so I'll keep going down the list. 1 times negative x squared over 2 factorial, which is negative x squared over 2 factorial. Next, we have the x term, so x times 1 is x. X times negative x squared over 2 factorial becomes negative x cubed over 2 factorial. Our third term, x squared over 2 factorial times 1 becomes x squared over 2 factorial. And our last term, x squared over 2 factorial times x squared over 2 factorial becomes x to the exponent 4 divided by the 2 denominators, 2 factorial times 2 factorial. Now, what I like to do in this is to simplify it. Okay, so take each of the terms and combine them when they have the same x value and exponent. So we have, and I also like to put them in order from lowest exponent to highest. So what we have is 1 plus x, that eliminates our first 2 terms. For x squared terms, we have a negative x squared over 2 factorial and a positive x squared over 2 factorial. So those two will cancel. Our x cubed term, we simply have x cubed over 2 factorial, which is the same as x cubed over 2, or 1/2 times x cubed. Okay, remember to keep the negative because it's negative here. And our final term is plus x to the exponent 4 divided by 2 factorial times 2 factorial, okay, which is 4. So that gives us plus 1 over 4 times x to the 4, okay? So it's as simple as multiplying them together and then simplifying by collecting like terms. So let's look at a second example of multiplying two series together. So find the series expansion for sine x times cosine of x, okay? Again, we have from that table at the start of this piece of the lesson that the expansion for sine x is equal to x minus x cubed over, 3 factorial plus x to the exponent 5 over 5 factorial plus, and then the terms keep going. Cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus, and then it also keeps going. So if we're multiplying these together, if we have sine x, cosine of x, that's the same as taking these expansions, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. So that's the sine x expansion, and multiplied by the cosine expansion. 1 minus x squared over 2 factorial plus x to the exponent 4 over 4 factorial. And those keep going. But you can see in the previous example, one of these had 3 terms and one had 2. So we ended up with 6 terms that we had to simplify. Now that we have 3 in both of these, you're going to end up with 9 terms that we then have to simplify. Okay? So again, as you expand it out, it becomes a more accurate representation, but it's also far more complicated to simplify. Okay? So at this point, with around 3 terms each will be where I kind of cap it for you. So you're not just multiplying them out and doing a ton of algebra just because I added extra terms. All right. So if we do this, again, remember, for each term in the first bracket, we're going to distribute by multiplying it by each of the terms in the second bracket. And we'll do that for all 3 terms. So starting with the first term, x, we end up with x times 1, which is x. X times negative x squared over 2 factorial becomes minus x cubed over 2 factorial. X times x to the exponent 4 over 4 factorial becomes plus x to the exponent 5 over 4 factorial. Then we start with the second term, negative x cubed over 3 factorial. So negative x cubed over 3 factorial times 1 is negative x cubed over 3 factorial. Negative x cubed over 3 factorial times the second term, x squared over 2 factorial. Okay, again, they're both negative, so that becomes positive x to the exponent 5 divided by the 2 denominators, 3 factorial times 2 factorial. Next we have negative x cubed over 3 factorial times x to the exponent 4 over 4 factorial. So that becomes negative, because you have a negative and a positive, x to the exponent 7 over the 2 denominators, 3 factorial times 4 factorial. Okay? Our last term in the leftmost bracket, x to the exponent 5 over 5 factorial. Multiplying this out, we get x to the exponent 5 over 5 factorial times 1 gives us plus x to the exponent 5 over 5 factorial. X to the exponent 5 over 5 factorial times the second term, negative x squared over 2 factorial, becomes minus x to the exponent 7 divided by 5 factorial times 2 factorial. And our last term, x to the exponent 5 over 5 factorial times x to the exponent 4 over 4 factorial, which becomes plus x to the exponent 9 divided by 5 factorial times 4 factorial. Okay, so you see it's a lot of terms. All right, so what I recommend doing is placing them all like this. Okay, just multiplying them all out in order and then collecting them together. Okay, the other piece you can do is I've left these as factorials. So what I do now is multiply the factorials out. So you can either put them in your calculator as, 2 factorial is, 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. But oftentimes on most of your calculators, there should be a factorial button. So this factorial symbol looks exactly like the exclamation point. Okay, that's what the factorial symbol looks like. So oftentimes you can just simply type 5 and press the factorial button in your calculator to calculate them. Okay, both of those is up to you. So what I'm going to do here is I'm collecting these terms and I'm going to do them in order. Okay, from the lowest exponent, which would be this x term, to the highest exponent, which is the x to the exponent 9. At the same time, I'm going to just expand out the factorials, okay, so they all become fractions. If I do that, I get x, and I'll kind of cross them out as I go with a different color. And we don't have any x squared terms, but we have a couple x cubed terms. We have minus x cubed divided by 2 instead of 2 factorial, so that gets rid of this term. And we get minus x cubed over 3 factorial, which is 6. Okay, so again, I like to cross them out to know that I've gotten rid of each term, or that I've brought each term into my next line for a solution. Next, I would look for x to the exponent 4, which there are not any, but there's x to the exponent 5. So starting with that, okay, I have plus x to the exponent 5. In this case, the first one's divided by 4 factorial, which is 24. Okay, so that crosses out that term. Then I have x to the exponent 5 divided by 3 factorial times 2 factorial, which if you write that out gives you plus x to the exponent 5 divided by 12. That gets rid of the second term. Our third x to the exponent 5 is x to the exponent 5 divided by 5 factorial. And that is x to the exponent 5 divided by 120. Again, that's knowing that 5 factorial is 120. Or you could multiply it out using this. Okay, so that gets rid of our last x to the 5 term. Now, we don't have an x to the exponent 6, we have an x to the exponent 7. So our first term is minus x to the exponent 7 divided by 3 factorial times 4 factorial. Okay, and that comes out to 144. That gets rid of this term. And our last term is minus x to the exponent 7 over 5 factorial times 2 factorial, which is 240. Okay, so that's our x to the 7 terms. There's no x to the exponent 8, but there is an x to the exponent 9 term. So we have plus x to the exponent 9 divided by 5 factorial times 4 factorial, which, use your calculator for this one especially, 2,880. So now we can simplify these. You can either put them in as decimals, or what you can do is you can add each of them up or collect the terms using your calculator, and most of your calculators will have a button that actually converts that decimal back into a fraction. Again, it's totally up to you for how you want to do them. So simplifying this, this becomes x, okay, minus 2 over 3 x cubed. Okay, so that's combining these terms. Then we have plus 2 over 15 x to the exponent 5. That's combining these three terms. Then we have minus 1 divided by 90, x to the exponent 7, combining these two terms. Okay? And lastly, we have plus x to the exponent 9 divided by 2,880. Okay? Because we do not have another term. It's just a single term. Okay? So multiplying these out works. It's just a lot of algebra. All right? But what you can see is to find the integral of this final answer is relatively straightforward, right? Because we have all terms that are, it's a large polynomial with x's raised to an exponent. All of those would use the power rule. Remember, the integral of some function x to the n is equal to x to the n plus 1 divided by that same exponent, n plus 1 plus a constant. So all of those can use the power rule, as opposed to, remember in Unit 2, when we had sine x and cosine of x, and how it changed depending on if they were squared, if the terms inside were different, and how that worked. It doesn't matter here. They could be multiplied out, and what you're going to end up with is a polynomial instead of a bunch of trigonometric functions. So this piece is a pain, I will admit, to do the algebra, but the answer at the end is worthwhile in terms of finding the integral because it's much faster. So our final case is using series to perform integration. So you can use it to approximate integrals of complex functions. And I say approximate because, again, unless you expanded out every term in the series, you're not going to get an exact answer. But a lot of times when the values of x are small, the Maclaurin series can provide a very accurate answer with very few terms. In this case, we're only going to look at the first three terms, which has been the typical kind of standard we've done throughout this lesson. So let's say we have an integral from 0 to 1 of e to the 2x dx. Now this might seem like a simplified example because I can tell you that the integral of this is 1/2 e to the 2x plus a constant which you can evaluate at 1 and 0. Okay, so you know that, but this could work for more complex functions like our previous example where we had sine of x and cosine of x. Okay, so it can work for more complicated examples. I just happen to be giving you what is one of our easier integrals. So if we want to do this using series, we can start by expanding it out as a power series. Remember, we did e to the 2x already. It was 1 plus 2x plus, in this case, 2x squared over 2 factorial, and we would keep going on. Simplifying this, 2x squared divided by 2 factorial. This is equal to 4x squared over 2, or 2x squared. So you'll see that is what I have placed here in the brackets. So we can rewrite this integral as the integral from 0 to 1 of e to the 2x dx as the integral from 0 to 1 of 1 plus 2x squared plus, and then always the dot 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 for more terms. In this case, we only have to integrate the terms that are showing in here though, right? Because again, we're getting to an approximate answer. So I will show you what this approximate answer is, and then we will compare it to what the answer would be if you actually used the integral here, or if you knew the exact integral. So keeping again with what we had, remember we had that the integral written as a series was 1 plus 2x plus 2x squared, and it keeps going. So using the power rule, remember the integral of a function x to the exponent n is equal to x to the exponent n plus 1 divided by that same exponent n plus 1 plus a constant. So integrating each of these terms, the integral of 1 just becomes x. The integral of 2x becomes x squared. The integral of 2x squared becomes 2 over 3x cubed. And then that would be plus the remaining terms plus a constant. Evaluating that now at 1 and 0, we get our first one is Substituting in 1 for x, we get 1 plus x squared, which is 1 squared, plus 2 over 3 times 1 cubed plus a constant, minus, now at 0, it's just 0, which cancels out. 0 squared cancels out to 0, and 0 cubed cancels out. So you're left with just minus a constant. So the constants cancel. And what we're actually left with is 1 plus 1 plus 2 over 3, or just these three remaining terms at the front here, which is actually equal to 8 divided by 3. So you can see we can use this to approximate the value. As we added additional terms, this number would become closer to the actual integral that's written here. Okay, so let's look at a different example. Evaluate the integral from 0 to 0.2 of the square root of 1 plus x dx. So what you're seeing here is a different series from the ones we've talked about, but one that can also be expressed based on one of the ones you see in that table from the start of this part of the lesson. So we can rewrite this as the integral from 0 to 0.2 of 1 plus x to the exponent 1/2 dx. Okay, remembering that you can write a square root as a fractional exponent. Now, if you do that, what you notice is there's another series on the table. And what it shows, okay, is it's 1 plus x to the exponent n. And what it showed was expanding that out, you got 1 plus n times x plus n times n minus 1 divided by 2 factorial x squared, and then it keeps on going. So what we see here is we see an x term in here and an x here, a 1 here and a 1 here. So that all matches. And what we see is the exponent 1/2, meaning that n must be 1/2. Okay? So what we can do is we can actually use this expansion and just substitute in the value for n here. We don't have to change the value of x because it matches what's in this initial series. Okay, so if we do that, what we end up with here is 1 plus 1/2 times x plus 1/2 times 1/2 minus 1 divided by 2 factorial, which is 2, x squared, and then plus the remaining terms. Okay, if we simplify this, we get 1 plus 1/2 times x. The next term, you get 1/2 times 1/2 minus 1, which is negative 1/2. That gives you negative 1/4 divided by 2, which gives you minus 1 over 8 x squared. Then you have your remaining terms. So what we can do is substitute these in instead of the 1 plus x to the exponent 1/2. If we do, we get the integral from 0 to 0.2 of 1 plus 1/2 x minus 1 over 8 x squared plus the remaining terms dx. Now, remember, using the power rule, we can integrate this. And if we do that, what we get, okay, is x for the first term, because the integral of 1 is just x, plus 1 over 4 x squared, minus, so we have 1 over 8x squared, that becomes 1 over 24 x cubed, and then obviously plus the remaining terms and plus a constant. And that is evaluated at both 0.2 and 0. If we do that, we get 0.2 plus 1 over 4 times 0.2 squared minus 1 over 24 times 0.2 cubed, and then plus the remaining terms in a constant, minus, okay, now everything evaluated at 0. So the first term, x, just is 0, plus 1 over 4 times 0 squared, minus 1 over 24 times 0 cubed, plus the remaining terms and a constant. So all of these 0 terms will go away. A constant minus a constant is simply 0. So we're left with just these 3 terms here. And if you multiply those out, you get 0.2097. Okay, so you actually get a number. Again, every time you have bounds here, we talked about this in Unit 2, you will always end up with some kind of number. What you're going to see in these is it's not going to be the neat and tidy in fractions. So more often than not, you're going to have to use a calculator to get this final answer. Okay. All right. So that was called a little bit long for a lesson, but it all covered the same properties, which are those power series. So these you'll start to become more comfortable with, and I say this every time I get to the practice problems, but practice, 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 okay? We have more series that we're going to introduce in later lessons. So the more you can become accustomed to the differences in each one, the better you'll be for them. If you have any questions, please send me an email. Thanks.